I do not know. I mean, I see 20 people. What is it today? Arkady vacation day or something. I do not know. Have you heard of it? If you are here, guys, naturally, I would like to see your faces. I mean, I see fewer and fewer of them. That's not a good tendency. Turn on the camera so I may look at you. You know, by the way, what is my my avatar or my picture here? Right? If I turn off the camera, you see what I am. Another thing you should be aware of, guys, is you see, I am considering, but we'll see if that will be necessary, but I am considering to keep your cameras on as a requirement for the final, right? Because I noticed some people begin to start some sort of WhatsApp groups. That's all wonderful, of course, but you understand, then I'll be a big member there. Good? All right, so exactly, Little Red Riding Hood, but I'm more so the big bad wolf. All right, guys, so if you are finding the material, as I explained it, difficult, my German friend that I enticed to go to the morning lectures, so she was reading this type of book. This is Calculus for Dummies, right? I do not know if that's a good book or not. I never read it, but maybe it explains some of the material in a simpler way, slower than I do, and you're welcome to try. I might post this book on my site, but you can, of course, find it here. I'm typing in my message. You can just go to Jen. You see, that's the website where you can find many good resources, including Calculus for Dummies, if that is helpful to you. Good. So I did my best. I wanted to find one, but I could not find the copy in German, so it's only in English, unfortunately, there. Now let's get back to our topic. Do you remember, guys, what is the tangent line? So here is that idea. The derivative at the point A, we're going to call it derivative. It's the ratio f of x minus f of a over x minus a as x goes to a. Now, what it measures is the slope, right? You see the point Q? I'm sliding point Q closer and closer towards the point P. And as those points merge, the secant line looks like it's just touching the graph at one point. Leibniz had a much better notation. The prime notation, it's Newton's notation. Good. Leibniz had the notation dy over dx. Dy over dx. Good. Now, why is that notation much better, guys? Because look at it. When you zoom in, look at it. When the point Q is very close to the point P, look at it. You look at the magnifying glass, you will see a very short horizontal displacement and a very short vertical displacement, which will represent the slope. So little dy over little dx is change in y over change in x. All clear? Now, we will do right now an exercise, and you will tell me which of those two definitions of the derivative is the best one to use. Okay, so first definition we learned is limit as x goes to a, f of x minus f of a over x minus a. Now, so you can do it. You can also create another definition. Look at it, guys. Instead of writing x here, I can write x minus a plus a. You see that? X minus a plus a. And then x minus a, it's the difference between x and a, and I can label it as h. I can label it as h, and the denominator I can label as h. And in this form, look at it, if x goes to a, then h goes to 0. So we can say limit as h goes to 0 of f of a plus h minus f of a over h. In this notation, I am speaking about, it's called perturbation. You see, it's basically an imperfect a here, right? It's an imperfect a. It means a plus something that is very close to 0. That's an imitation of a. F at imitation of a minus f at a divided by the difference, by the error. The formula makes sense to you, I hope, guys. Yes? And in Leibniz notation, it will be simply the derivative at x of df dx or dy dx at x equal to a. Hello, Avraham. Nice to see you here. So hope you can all take part. So guys, you might imagine that that changing notation to this symbol or to use the prime, it's not a big deal. But actually, you see, and think about it, there were amazingly great mathematicians in both England and the continent. Continent means Germany, France, in Europe. Good? But because there was an argument between Leibniz and Newton over the origins of calculus, who invented calculus? Was it Leibniz or was it Newton who discovered it first? Because of that, the British did not adopt that notation. And mathematics over the British. Avram, what holidays today? Is it Purim?
Yeah, today's Purim, so they're just about to, they read the Megillah, so.
All right, well, enjoy your holiday, watch the recording once you have the chance, right? But if you want to just scare the children, you can show them me, right?
Right here, we have one of.
Right? All right. Take care. My German friend is saying that that I remind her of this monstrous teacher that she had in school, you know, Volker Hauwe. So she always compares me to him. So I get very proud. So here we go, guys. So back to this topic. Again, you see, you have the British Isle where Newton's notation was used, and you have the continent where they preferred Leibniz notation. Just because of that notation, the progress on the British Isle lagged by 50 years. Can you imagine? Just because of the wrong notation. And why is that the situation? Is because the notation of Leibniz reminds you of the lowly origin of the derivative. It's just slope. Also, the German word for derivative is Ableitung. Here, let me write it for you. It's good for you to remember, maybe an extra credit. Ableitung means lead off, roughly speaking, right? It reminds you that what happens is that when you depart the curve, you know, if you think about physics of it, right? If a rocket flies along a non-linear curve, that means that the rocket is exerting some energy or some force is acting on that rocket. And if the rocket stops that force, it will fly along a tangent line. Okay, it would be let off the curve. And that's a very good word. Derivative, you know, I mean, it's not so intuitive what it refers to, but Ableitung, lead off, a very nice description. Okay, so always think about the lowly origins of the concept. What is the derivative? It's merely the slope of a line, nothing more. So dy dx reminds you that it's the slope of the line, and it reminds you that it works just like a fraction does. Okay, and if you understand fractions, then you understand a lot about slopes. Good. So let me try to illustrate the notations, guys. You see there is notation 1. It's the notation I taught you. Let's try to do this derivative using notation 1, please. Do you understand what I'm asking you to do? I'm asking you to calculate at any f prime of a. I'm asking you to calculate limit as x goes to a of f of x minus f of a divided by x minus a. calculate it using this notation. Let's see what happens. Exactly. Thank you, Aaron. Come on, guys. In the morning class, I had at least 10 people turning on the cameras. What is happening here? Jeffrey Zhang, maybe you can turn the camera on. Nicole, I would be happy to see you. Brianna, wonderful to see you if I can. Dauda, consider turning the camera on. Safa, turn the camera on. Great. If you cannot, guys, I understand. I mean, maybe you're in a bad situation, but come on, guys, let's not exploit that. Thank you. Thank you, guys. Wonderful. And if you're done with the first notation, calculate it using the second notation. Thank you, Safa. Enrique Mendoza, if you are available, turn the camera on. Tre la force. Toju Esun. Kevin Bravo. Brian P. Come on, let's make it fun. Wonderful, Sandra. If you're done with notation 1, do it with notation 2. Okay, guys? Notation 2, if you don't remember, it's this. Alexandra, wonderful. All right, are we ready, guys? Let's do it using notation 1. It should, once you are well trained, it should take you less than a minute to solve it. Okay, that's what you strive for, less than a minute for such a problem. Now, let's see how that's done with notation 1, guys. You see, minus 2x squared plus 5x plus 13. Now look what happens here, guys. So this is the function at x minus the function at a, divided by x minus a. That's just the setup. Now realize, guys, what happens here. Realize that when you group like with like, you see here minus 2x squared and minus 2a squared. What always happens is that the constant is factored out and you have x squared minus a squared. Okay, next is the power of x to the power of 1, right? So we have 5 factored out and it's x minus a. 13 minus 13 is 0. You understand that, guys? Let me just be sure that you can factor it out very fast. Suppose, guys, just a second, that's a sidetrack. Can you tell me what will be the numerator right away if the function, the first stage, the numerator, can you kind of right away skip to this line if the function were, let's say, minus 13x cubed plus 7x squared plus 12x minus 5. Could you, for that function, tell me that's the second step right away for the numerator? You see what it should be? Oh, great, Brianna. Nice to see you. Thanks. You see, we took a segue. I just want to see if you understand that you can very quickly and efficiently parcel it. So here is what you should be getting. If that was the function, it would be limit as x goes to a. It should be minus 13. Exactly. 5, be careful, 5 is wrong. The last, the constant will be gone. Yes, Grant, exactly. Exactly, here you go. So it's minus 13, difference of cubes, plus 7, difference of squares, plus 12, difference of power 1. Yeah? And then 5 minus 5, no x minus no x, it's 0. So it will be like this. Practice and notice that that's the pattern. It's obviously always what's happening. Good? So you can always skip the first step once you get very comfortable. So now we're here. Look what I'm doing now, guys. I am factoring x squared minus a squared into x plus a, x minus a. Yes? And notice now that I have x minus a and x minus a, which I can now, it's now product. It's like distributive law. I factor it out. And what am I getting, guys? I am getting minus 2x plus a plus 5 times x minus a. It's now product divided by x minus a. I simplify x minus a and I push the limit. Now there is no longer denominator or x minus a here. That's what we have left. X here becomes a. So it's minus 2 times a plus a. That is minus 4a plus 5. Minus 4a plus 5 is what we're getting. Yes? Now notice I spoke and I was explaining how long does it take to do that, guys. If you train yourself, it takes no time at all, right? It takes a few seconds to figure it out. There is no plus 5, Jeffrey. You mean in my case, right? The plus 5 is because look at it, I factored. Do you see the 5 here? I am just, what are you asking, guys? You're asking this. You're asking me if I have AC plus BC, why is that equal to A plus B times C? That's what you're asking me. You see that, where is my A? My A here is this part, and my B here is this part, and I factor out X minus A. That's my C. I'm just using the distributive law, guys. You understand? Yes, guys? Guys, you should not be sad. This type of thing you learn, well, in school before you take calculus. So when you ask me when is the exam and why is it delayed, is because I try to teach it slow enough so that you can hopefully catch up to this level, to what is supposed to be prerequisite. All right, so we have minus 4a plus 5. What it means, guys, is that to calculate the slope at any point a, I just multiply by minus 4 and add 5. So for example, if I wanted the slope at 1, at x equal to 1, I just take minus 4 times 1 plus 5. Good? Now, has anybody tried doing it for the second method? Here it is. Here is the second method. It would be nice, guys, if before I speak about it, you try to do it yourself. There is a point. I want you to notice something. I want you to tell me which of the two procedures is harder. Which of the two procedures is harder, I want you to tell me. And then also why one procedure is harder than another. You understand what I'm asking, guys? Now, the same thing. We already know the answer is minus 4a plus 5. I want you to obtain that answer using the second procedure. Give me a second, guys. I am back. Yes, well, thank you, Aaron. All right, guys, so try it on your own. Guys, I'm waiting another 5 minutes if you have to, okay? I want you to try it on your own, the second procedure. How are we doing, guys? Progressing? Two minutes. Stay after class if you want to practice that more. Jomero, you made some mistake. It cannot be -5, and we will understand why in a moment. Hello, James. All right, time's up. So let's look at how that works. Here is the second equation in action, guys. So what I have is, instead of x, I plug a plus h. Do you see that? And then, of course, because I see a plus h, I see parentheses. Psychologically, I feel like I want to expand the parentheses. You see, those two definitions, I hope you understood how I obtained them. They mean mathematically exactly the same thing, but some of you study psychology. Psychologically, they compel you to do something entirely different. So here you're expanding it, and you get here -2a squared plus 2ah plus h squared. Here you distribute the 5, so it's 5a plus 5h, right? And here I just eliminated 13. You see, I have here minus is distributed, so you have 2a squared minus 5a and minus 13, but there was a plus 13, so I eliminated them. Yes? Then I begin to cancel out things that I can remove here. Do you see here? I can say minus 2a squared can be canceled with 2a squared, 5a with minus 5a, and this is what is remaining. Do you see that? This is what remained. In the numerator, here I can factor on h. Once I factor on h, look at it. I cancel out one instance of h. I have minus 4a plus 5 minus 2h. And when I push h towards 0, I am left with the same answer, naturally, minus 4a plus 5. Now, I hope you see, guys, that the second equation was more difficult to apply. It took you longer to solve it using the second equation. Now, why was that the situation? Let's for a second look what happens if we just set up, not even do anything, but just set up the derivative for the following problem. You see, we have x squared plus root 5x to the 4th plus 1 divided by x squared plus 4. We are not going to solve the derivative right now, but we're going to set up the limit using notation 1 and then using notation 2 and see what happens. Okay, so using notation 1, this is the way it looks. Do you see that? And if you count the number of symbols that you used 33 symbols to just write this one equation. Now, if you use the second equation, the second notation, look at it. Here it is using the second notation. You just plug, instead of x, you plug a plus h. And this is the way it looks. Just by writing it one time, you use 10 more symbols, 43 symbols. Just writing it once. When you expand parentheses, especially if it's high powers, you will, each new line that you add, you will write at least 10 symbols extra, probably more on average, you know, when you expand it. So the expression looks more bulky. It's easier to forget some symbol and make a mistake. Yes. And also, just when you are writing, each symbol takes you some amount of time to write. You see, so if you actually follow the second notation, you are, even if you do it well, you are probably going to be twice as slow and more likely to make mistakes. Does it mean that the second notation is not useful? No, it does not. I can give you a sort of rule of thumb. There is a preference between those equations. If you are dealing with algebraic functions, which is the only thing we have covered so far, the first notation is preferred. But if you are dealing with trigonometric functions, exponential functions, you will see that the first notation might stump you, but second notation leads to a good result. I mean, they are the same mathematically, but one is impelling you to go one way psychologically. Another one is impelling you to do something entirely different. There is a different compulsion. And that means a different philosophy of solving the problem. Do you understand, guys? So it matters which notation you pick. And of course, later on, the people that read the book, they tend to pick the second notation, so they don't listen to me. All right? Pick the notation that's best, because that will give you a fastest solution for all algebraic expressions. Okay, guys? Let's do another quick practice, okay? Would you please tell me, if I ask you to take the derivative, so let's say if the function f of x equal to root of x, would you please tell me what's f prime of a? And before you begin, which notation do you prefer? Notation 1 or notation 2 for this question? Before you begin, could you tell me which do you prefer? Yes. For the reason, just if you ever did anything in programming or write anything up, if you have to write more symbols, it will slow you down, and also harder to keep those symbols in memory. So you're more likely to omit something. Yes, but Sophia and all of you guys, you understand that those notations I never memorized. I just understand why both of them are mathematically equivalent, and that's what we will try to train. So notation 1 is this. And notation 2 is this. So you should be able to see that the second notation is directly related to the previous formula. It's they're speaking the same thing. This you should solve, guys, in 1 minute. Exactly, Aaron, good. All right, times is up, guys. So let's see how that's solved. One half root a, exactly. So why does it, especially for this one, should take so little time? You have limit as x goes to a of root x minus root a, x minus a. Good? Exactly, Grant. You see that, guys? Now, afterwards, you can multiply by the conjugate, but I will show you another thing that is more general, and we will soon use it. I am going to factor the denominator. Now, how can I factor the denominator? I can do it this way. Well, look at it, guys. I can write limit as x goes to a of root x minus root a divided by root x squared minus root a squared. Do you agree? I wrote the same thing because both x and a have to be positive. There is no problem here. And now I can factor out the denominator. That becomes root x minus root a times root x plus root a. On the top, it's root x minus root a. This goes away. Yes, it goes away. And what do we have in the limit? Now the limit is simply root x becomes root a. So we have 1 over root a plus root a, which is 1 over 2 root a. Wonderful. Let's do one more. One more. And we can do a lot more in office hours if you stay. Tell me, please, if the function is f of x equal to 1 over x squared, calculate as quickly as you can the derivative at a. And try to do it faster. I'm waiting no more than 4 minutes. Toju, it's not right. Okay, John, Michael, Michael, wonderful. You did it. To you, John. Okay, Erin. Fine. Great, Grant. Very proud. Let's see if anybody else joins the club. Brianna, congratulations. Well, careful, Brianna. Is there a 3 power or a minus 3 power? All right, guys, time to do it together. Ready? Yes, then you're right. So we set it up. Limit as x goes to a. What do we get? We get 1 over x squared minus 1 over a squared divided by x minus a. Which, what do I do, guys? When I see a difference of two fractions, I'm right away tempted to subtract those fractions. So I multiply this by a squared on both sides and this by x squared on top and bottom. And I get a squared minus x squared divided by a squared x squared. And if I divide by x minus a, that is the same as to multiply by 1 over x minus a. Good? You should be able to get to that point immediately, guys. Two fractions, you know how to subtract one fraction from another. They have to have the same denominator. So one requires top and bottom multiplication by a squared. The other requires top and bottom multiplication by x squared. Good. Now I can factor out a minus. So look at it. I can write it as minus x squared minus a squared divided by a squared x squared times 1 over x minus a. And then I can factor that further. I can write it as minus x plus a, x minus a, divided by a squared x squared times 1 over x minus a. Now I am able to cross away x minus a and taking the limit. You see, I didn't write limit, I kind of omitted it, but you understand. Now when x becomes a, what's happening here? I will get minus a plus a divided by a squared, which becomes minus 2a divided by a to the power of 4, which is minus 2 divided by a cubed, Good? Again, guys, if you find that's difficult, you stay after class where we do more examples. Okay, guys, now you notice what those formulas indicate. So they give us a formula, right? They give us a function, right? What to do with the point, if I'm zooming in, so if I take a point xy on the graph, then if I know the x coordinate, I know how to calculate the slope of the tangent line. So for the root function, if I want to zoom, if I want to calculate the slope at the point a, all I have to do is I take 1 over 2 root a. Yes, that's going to be the formula for the slope. So in order not to move from x to a, we are going to make a slight modification. Okay, guys, so hopefully it's not confusing, it's just notation. Because I mean, I see that f of x is a function of x. I want the derivative f prime to also be a function of x. So I make x that fixed point rather than a. So then for that, I need to make another letter, right? Another letter is going to x. So f prime of x is z approaching x, f of z minus f of x divided by z minus x. And the second definition is, as h goes to 0, it's f of x plus h minus f of x divided by h. Good? let's see if you can find f prime of x for this function. 5 minutes, guys. X squared plus 3 root 9 minus x. Find me, please, the derivative of that function in terms of x. Yes, so good. Erin, you got it. There is a minus on, you wrote minus, yes, good. And Brianna, you got it. Okay, guys, let's do it together. Ready? So here is the setup. Do you see what I do? Hopefully it's not a very confusing thing here. I just replaced x now is what used to be a. Z, in other words, x is my fixed point at which I want the derivative calculated. Yes? The derivative calculated meaning the slope of the tangent line calculated at that point. X now is the coordinate of the point P, the x coordinate of the point P. So then I say z going to x, the function evaluated at z, minus the function evaluated at x divided by z minus x. Same as before, you group like with like. Look at it. Z squared and x squared I group together. And I move the z minus x underneath. Here I group root of 9 minus z and root of 9 minus x together. Okay, so this, guys, this step, you should almost have it immediately. It's just algebra, right? I mean, I'm sure some of you are confused. Why is z minus x now used to have 1 z minus x, now you have 2 z minus x. That means, if you are confused, that your algebra is limping. That means you have to practice a lot of those. You can actually practice them while doing derivative. Right? Doing those questions, you can practice the algebra. So it's, again, distributive law. Z minus x goes here and z minus x goes here. Here we have that line. Next, what I can do is this part I can factor out and cancel away z minus x. Z is the sliding point. They don't come from anywhere, guys. You have to understand what we're trying to do here. You have to have a description. Right? What am I doing here? I have the point Q. Let me just see if you understand what is the Z, right? So we have this function, right? Point P is the point at which I calculate the slope of the tangent line. What are the coordinates of the point P? Because I want to be able to do it for every coordinate. Before I used to have it A, f of A, but now I decide to make X, f of X that coordinate. It's just a language thing, you understand? It just, I mean, I designate by x, f of x, the fixed coordinate. That's the coordinate at which I will zoom in. Good? So that is x, f of x. Now the moving part is going to be the point Q, which is z, f of z. Right? There is no such thing as a, there is no such thing as x. I can use all sorts of symbols. What's the idea? I'm speaking of a fixed point and another point Q that I will move towards it. I can use any letters to describe that. Okay, so then what do we have here? We multiply by the conjugate, simplify, and when we simplify, we have 2x plus this expression, we cross away z minus x, and look at it. Now I can transform all the x's, all the z's into x. You see the z is becoming x, so you have now 2 root 9 minus x. We have this formula. You should not go away from this class if you are not able to do that fast, and you are not only doing it fast, guys, but understanding what you're doing. You see, when you're asking where is the z coming from, where is that means that you are somewhat looking very close to the ground. You do not see the picture, and seeing the picture is the difference between making this 500 pages look like 1 page or less, or just being lost in the forest. You understand? You have to basically, if your eyes are in the ground, you will not be able to move anywhere. If you're in the dark, you cannot go from one room to the next. Right? So you have to have a sort of clear sight for what you're doing. And let's now try to develop that clear sight. Now we're going to investigate the relationship between the derivative and the function, right? How are they related exactly? Okay, guys. And for that, let me ask you this question, guys. Do you see this graph? This is the graph of y equals x squared, yes? Could you tell me what shape will the graph look like if I zoom at the point 0, 0? Do you see this point 0, 0? What is going to be the shape of the graph when I zoom in at 0, 0? Okay, a line. Two people see that. A line, straight line, a few people say. Let's begin to zoom in, guys. Let's begin to zoom in. Look what happens here. You see here is 1 and 1. I'm zooming in. Do you see what's happening? Do you see that? I get a flat line. How many of you predicted? I see 3 of you predicted that I will see a line, but not everyone. Yes? Now, would anybody, before I continue, guys, so let's see just by comments, tell me, did you predict it and didn't answer? How many of you saw that it's going to be a line? I see 4 people, and the rest of you, were you surprised by the result? You saw it. Now, maybe this is a good point, and you will remind me, geometrically speaking, what's so significant about the derivative? If you had to explain to somebody on the street, why would anybody be obsessed about derivatives? Geometrically, I would like an example, right? Why is that obvious that it will be a straight line here? And in general, maybe why, what is the derivative again, guys? What is the tangent line? Why do we care about a line tangent to the curve? Would anybody like to speak?
It's easy to calculate the slope of the line than of any complicated shape.
But why would we care to calculate slopes to begin with? Right? I mean, we can calculate stuff, but why calculate it?
We can calculate a change over a very small fraction of interval, where basically the change is almost negligible.
Yeah,
if we need to calculate like the, let's say, like the velocity of something, right? What you were saying.
Let's zoom out and see this, guys. What can you think about a curve? Right? You look at a curve, and a nice way to see it, see what the curve might be made out of. You can think of it as made out of a chain of line segments. Right? So a curve is complicated, but it can be viewed as made of chain of line segments. Okay? And when you're traveling along a curve, you can imagine that the object moves just at least a little bit along a line. And then if a force applies on it, Grant was saying something that it changes the line from which it moves on, right? So the derivative kind of, if force stops impelling the object to travel along a curve, the object will just move away. And the object always feels or thinks that it's on a straight line segment. Do you understand? Now, let me try to, again, guys, so some predicted that the line will be horizontal. It will be y equals 0, as Grant said, I think, right? And a few other people said. Do you understand why that would be the situation, guys? So what is that, the zoom in looks like what? Let me zoom in at another point for a moment. Let me zoom in at the point 2, right? Let's zoom in at the point 2. You see the point 2? Here it is. You see that the line I'm seeing is no longer horizontal. It's a different line. Yes? Do you know what is this line, guys? Could you tell me what is this line in terms of what we were studying? This happens to be the tangent line. Now, how do I know this happens to be the tangent line? think about what happens, guys, when I zoom in. When I zoom in, let's say at 2, look at it. I see here a lot of values, right? A lot of values. If I am looking at this distance of 2, I see a lot of values of x, and I can see a lot of different lines emanating from this point. So here at 2, I see, for example, this line, but I also see from this point towards 2, I see that line, right? And I see many other lines that are not agreeing with each other, right? They have different slopes. You agree that? You see that, guys? Now, what happens if I zoom in? If I zoom in, I stop seeing points x that are far away from 2. Look at it. And I begin seeing points of x that are very close to 2. Do you see? Look at it. They are just a few tenths of a unit away from 2. I zoom in more. You see what's happening? You see? Look at all the values. If I make it the middle, look at all the values I'm seeing. They are all closer and closer and closer to 2. Yes? Which means that the 2 points on the graph that I'm seeing, guys, look at it. I'm seeing this point on the graph, and this point on the graph is, well, let's say this is just some x squared, and this point on the graph is 2 squared, right? So what am I seeing here? I'm seeing here x squared minus 2 squared divided by x minus 2, where x is very close to 2. You agree? Here, look at any x that I'm seeing in this picture. X is very close to 2, which is the same thing as saying limit as x goes to 2. Do you understand, guys? When you read the sentence, you have to imagine something. If I say limit as x goes to 2, what am I saying? I'm just saying calculate the fraction where x is just very close to 2. I'm not saying anything sophisticated. Yes? So what is that going to tend? As x goes towards 2, this will tend to the value 4, as you can calculate. So you're seeing a slope of 4. So for each 1 unit of horizontal motion, you will see a climbing of, you'll see climbing to 4 units. That's locally what you're seeing. And if you zoom in somewhere else, you will see a different line. You see here I'm zooming out, and as I'm zooming out, I make x far enough from 2 that I can actually see that there is going to be that it's curving. You understand why zooming in at a curve, I will see a straight line. That means that geometrically, guys, what is the significance of the derivative? If you look geometrically at any shape that's differentiable, that means when you come close enough to that shape, when your perspective is limited, it will look to you like a straight line. Was it important idea, guys? That Martin Luther believed that the earth is flat. Why did he believe that the earth is flat? Because, you know, the earth, if you think about the earth, it's a circle, right? Let me just give you a two-dimensional or one-dimensional, one-dimensional illustration of it. So that's, okay, 1 second. Here it is. You see that, guys? Here is a curve. Now let me zoom at this point. What am I gonna see? I'm zooming in and I'm seeing a straight line. Do you see that? That's exactly the illusion that you see about Earth when you look into the ocean and it looks to you like it's a flat plane. It just in higher dimensions, instead of a tangent line, it becomes a tangent plane. Okay. Now it always looks to you like it's horizontal because your perspective is like this. Your perspective is skewed, and we will learn the geometric perspective will give us a huge facility in understanding formulas. You understand? If you understand the geometric perspective, all lines look to you like the same thing, because this is a horizontal line if I view it like this, but it's not a horizontal line if I tilt my head. Good? The essence geometrically is that you are, when you zoom in at a curve, you will see a straight line. Now let's see if you understand that idea, guys. Here I try to illustrate what happens with a bouquet of flowers. Okay, so you see that there is, if you're looking at this curve, if you're looking up to this line, you can see the red lines that you can draw. There are many angles that you can make. The angle can be pretty obtuse. But as you are narrowing your view, as you're zooming in around the point P, your X is closer and closer to the value A, which means that the possible points on the graph that you're seeing have closer X towards A, which means that you are going to see the tangent line. We will check if you understand that idea. You see, you zoom in on a curve, you will see the tangent line. This is the illustration in terms of all the lines that you're seeing. If your point of view is wide, then you see lines that are not merging into together. But you come closer, you can see that all the lines are now making smaller angles with respect to each other. So all the possible lines, the bouquet of lines, merges and starts to look like one line. Do you get me? It's just that animation that I showed before, guys. I mean, right? Do you understand what I just explained? You do, right? Do you understand what I'm saying, guys? So let's check, guys, your intuition. If you understand it, this is what I try to show you, guys. You know, most formulas, and I'll teach you how to do that, right? Most formulas, if you can use this information, you did not read in a book. You come up with a solution on your own. You come up with your own formula, your own theorems. And you do that in physics all the time, right? So let's see if you can come up with with a very simple explanation. Tell me, please, do you remember what is continuity? What does it mean for a function to be continuous? It means that its graph is a connected curve, right? Its graph can be traced without lifting the marker of the board. It's a connected curve. It's one piece. And could anybody tell me what does it mean for the curve to be differentiable? So if I have a curve and I say it's differentiable, what do I mean by that? It means that if I zoom in anywhere on this curve, what I will see is what? If I zoom in at any point of that curve, I will see what? A line. No matter where you look, you will see a line. That's what differentiable means. You understand? It has to be very visceral. Good? Now let me ask you this question. If a function is continuous, sorry, let's do it this way. If the function is differentiable, does it mean the function is continuous? Answer yes or no and explain why is that? I said this, the function is differentiable. Is it continuous? Now you can say yes or no, but guys, you might forget it. What am I asking really? How do you know that, right? Would anybody care to speak?
Well, if there is, when we zoom in on this function, if it's differential, and there's going to be a line there, and it will be continuous because the line is, it just goes without a stop. There is no space.
Breaks. Exactly.
Yeah,
right?
breaks.
So it's very intuitive. The answer is immediate. It's going to, if the function is differentiable, it must be continuous. Do you understand what, forget about those complicated words. It just means this. Is the curve one piece? Well, if you zoom in anywhere and you see it at the point A, is there a tearing? No, because it looks like a line. And the line is not there's no tearing there. Yes? Zoom in anywhere else, it looks like another line segment. So differentiability naturally implies that the curve is connected. If it's differentiable at a fixed point A, then at that point it's also continuous, because zooming in at A, you will see one solid piece. Good? Anywhere you look, you see one solid piece. So if it's differentiable at any point A you can zoom in at, then it's continuous everywhere because there are no tearing. Guys, but now let's try to understand how the concept is communicated. Do you understand that part of mathematics, when people say mathematics is a language, what they mean by that is that you have an idea and using those symbols, you try to capture that idea precisely. Do you all remember, guys, what's the definition of continuity? Do you remember, would anybody like to explain what the definition is? Do you remember that it is limit as x goes to a of f of x equals to f of a? That means continuous at a. Do you see why that idea captures wholeness at that one point? Because if I look at the graph of such a function near the point a, if this is the point a, remember what we're trying to say, guys. We're trying to say that the function is defined at that point, and if you move from the left or from the right towards that point, if I move along that curve, look at it. Here is my x. That means bring your x coordinate closer to a. Your y coordinate, the point is defined as x fx, right? That point will be getting closer to a f a. I'm sorry if I kind of threw it at you. I hope you understand it, guys, right? I would not forget such formula because it makes sense to me how it communicates the idea of connectedness at that point. Does it make sense to you that it communicates that idea? Yes? It just, what I imagine is that I'm sliding my fingers along the curve towards the point A from left and right, and I'm merging my fingers when I'm sliding are supposed to merge in the same location. Mathematically, it just means that calculating limit produces the same result as plugging in the value a. Good? Now, let's try, guys, although it seems natural to us, I hope it seems natural to all of you, that differentiable means continuous. Let's actually prove it analytically. Do you understand what happens, guys? There are many things that appear natural to us, but then once we examine it deeply enough, we understand that we were fooled. Okay, so in mathematics, you are extremely obsessed about proving that what you're saying is correct from all perspectives that you look at it. Okay, there is an intuition that inspires your observations, but you must make the intuition solid. That even if you are sure that it's true, you have to prove that you haven't made mistakes and that your communication of the concept is actually accurate. It's saying the same thing. So here is what I am saying, guys. If the function is differentiable, you understand what? If the function is differentiable, then this limit if it's differentiable at a, this limit exists. It's equal to some f prime of a. So assuming that we know that this limit exists, do we know that this limit exists? You understand? I'm doing it no longer with intuition, but just as a robot, formally. Can you prove that this limit as x goes to a of f of x is existing? Let's do it together. Guys, you have to understand how this formalism is supposed to work here, right? So I need to understand what am I searching for. I am going to search in this limit in f of x, in f of x, I'm going to, let me actually do it on a separate piece of paper. Here, guys, you see, I begin, this is the limit I care about. This limit, I want to show that it equals to f of a. I only know this limit. This is my model. I know f of x minus f of a over x minus a. What do I do with this, guys? Look at it. So I want it to look like this expression. You understand? I have this expression. I want to make it look like an expression I'm familiar with. So what do? I subtract f of a, but I cannot change it. So I then add f of a. You all see what I'm doing, guys? I'm just morphing that expression into another that's very familiar to me. Can you tell me what's the next step? Denominator as wonderful. Sophia, you are seeing it. Denominator must be x minus a. Do you see, guys, what guides me? I need to know where am I walking, and then I know how to complete that procedure, right? So then I see, okay, this is limit as x goes to a, and then here I write f of x minus f of a, and I will use blue just to indicate it here. That is x minus a. And I cannot just include it here. If I divide by x minus a, I need to multiply by x minus a plus f of a. You understand what I'm doing, guys? I am just making my expression that I have look like the expression that I want, because for that I know the limit. Yes? So what happens here, guys? So I know by limit laws that this thing, it will approach f prime of a. This thing will approach as x goes to a to 0 plus f of a. So that means that the result of this limit is simply f of a, which is continuity described formally. Clear? You understand, guys, what I'm doing, right? It's extremely easy if I understand what the symbols mean, not just that they're just arbitrary symbols. Good. So that means that differentiability implies continuity. We saw that without any calculations. We saw that because zooming in on a curve, if it starts to look like a straight line, that means that in particular that curve is connected. It's one piece. And if it's connected, then it's continuous. That's what we were trying to capture. You understand, guys? So differentiability implies continuity. Now, I want another question, guys. Now, does continuity imply differentiability? And also, before you even try to answer, just think about it. What does it mean? The graph is connected. It's one piece. Does that imply that the function is differentiable? What am I asking? Could anybody, before even saying yes or no, tell me what am I asking about the graph? It's continuous. And I say, is it differentiable? What am I asking? No, I've said continuous. That means there are no holes, right? And I'm asking if it's different. If you zoom in, you see a line. Do you see a line when you zoom in? Differentiable means I zoom in, I see a line. You understand? I see animation, guys. right? It's not meaningless dribble to me. So now, if you understood what the question is asking, tell me please, does continuity imply differentiability? If I zoom in on a curve that's continuous, will I inevitably eventually start seeing a straight line? So Alexander says yes, Sophia says yes. What about the rest of you? Yes? I zoom in on a curve, I will start seeing a straight line. Do you believe that? Yes. But not just a statement, but explain to me what can happen, what can go wrong, guys. Right? Let's look at the picture. Here, guys, is I create a curve made of two line segments. Two line segments. You see that? Here is one line segment. I will write a formula for it in a moment, but here is one line segment. Here is another. Now, what do you think would happen if I zoom in at the left leg? What will I be seeing? So in other words, better said, what is the derivative at this point, guys? What do you think? At this point, the derivative is going to be what? Okay, I withdraw that question. I withdraw that question 1 moment. Look what happens here, guys. If you zoom in, forget about anything else. If you zoom in at the left leg, no matter how much you zoom in, what are you going to see? You are going to see a straight line. Do you agree? If you zoom in on a straight line, you continue seeing a straight line. Right? This straight line has a positive slope. So anywhere you zoom in, looks to you like you're observing the same slope. When you're asking what's the derivative, you're asking what's the slope of that line. Right? So you will see the same slope anywhere you zoom in here because you're seeing the same line. Those are like microscopic tiles, line segments that are all aligned together. Now, if I zoom in here, I will see a negative slope, another line. Yes? But if I zoom in at this peak, it remains sharp. Do you see that? It remains sharp and it always looks like a broken line. You agree? No matter how much I zoom in, it will look like an edge. It will have the same angle. No, you will, but the one dot will remain one dot. I will show you if you want a graph like that in a moment with a computer. But you cannot truly see anything with a computer. Those things are a bit abstract. You see, zoom in, it's going to be always a wedge. It's going to remain sharp. Okay. You have to kind of see only one line over the entire screen if you zoom in at that point and it's in the middle of your screen. You understand? So this function, no matter how much you zoom in, you always see the same wedge. It looks exactly the same. Zoom in at this peak, it looks like this original picture. Zoom in again, it would look like that original picture. You understand? The shape under zoom in doesn't change. It looks like a wedge. Good? Now, this is even worse, guys. I will show you that example in a moment as well. You see this? It's even worse because here the wedge is, you see, the sharpness is actually going to be steeper and steeper. You see, the angle between those points is going to be sharper and sharper and sharper. Let me show you this graph if you want, right? I will show you this graph and I will show you the other. Okay. So let's look at that one. So that would be here. You see that wedge? Now let me zoom in at this point. Do you see that no matter how much I zoom in, if I keep that point in the center, it will remain a wedge. Look at it. The picture doesn't change. You agree? Look at it, it's huge zoom already. Picture doesn't change. You see what happened here? Now let me show you the other picture of another wedge. So it would be, let's say, 1 minus absolute value x to the power 1/3. Aha! Look what happens here. Look how sharp it is, right? Before the angle was kind of, you could see it, it's the lines are kind of leaning against each other. But let's look at what happens if I zoom in, let's say here. You see, I zoom in at this point, it looks like kind of like a straight line. But if I move upwards, the line looks steeper and steeper and steeper. It looks like it has a much higher slope. You see that? So this is even worse. That's infinitely sharp. You see, this is this sharp and this is infinitely sharp. It's like point sharp, like a needle sharp. And so differentiable functions are called smooth functions, because when you zoom in locally, it looks like a line. It doesn't look like you would be cut. But non-differentiable functions will be sharp. This is the situation that would happen if a function is not differentiable. You can see from one side it's plus infinity, from another it's minus infinity. That's where it's extremely sharp. It's worse non-differentiability. Let me show you this function that I just graphed. This function is f of x equal to 1 minus absolute value of x. Now you remember what absolute value is. It's just x if x is positive, and it's minus x if x is negative. So I can write it as a piecewise function, guys. 1 plus x if x is less than 0, and 1 minus x if x is bigger than 0. Now that you see the formula, I'm going to repeat my question, guys. If I look at it, here is that 1 plus x, right? I'm actually going to ask you, what function am I going to see if I zoom in here? That's a comprehension check. You don't need any calculations. What function do I see if I zoom in at this point? Give me a formula of that function. If I zoom in at that point, what am I going to see? One plus x. 1 plus x, I will see. You know how I know I'll see what, because look at it, guys. How did I reason, or how did Alexander reason? 1 plus x. Let me show you how that is reasoned. Do you agree, guys, that when I zoom in on this curve is a line. So what I will continue seeing is that same line, right? If you understood, that's you have to really understand it, guys. The derivative is the slope of the line that I will see when I zoom in at it. And the tangent line, the equation of the tangent line, is the equation of the curve that I will see when I zoom in. The tangent line is that shape that you are seeing. Do you understand why? Because what you're seeing a line. Now, if you know the slope of a line and you know a point, and you have the point on the graph at which you're zooming in, then you have that equation of the tangent line. That's what you're seeing. Good. So that means anywhere you calculate the derivative, the answer will be +1. The slope is +1. Anywhere you calculate the derivative, the answer here will be -1. And at 0, it will be +1 and -1. The derivative curve is discontinuous there. Okay. So here I actually carry out the calculations. You see that? I carry those calculations, and you can see that from the positive direction, it's -1. From the negative direction, it's 1. You're welcome to try those calculations on your own. That was obvious without calculations, that the answer will be that. Clear? You see why? If you understand, guys, and that's what, again, I'm trying to encourage. Some of you do not understand what we're doing here. You might say, why carry those derivatives? Why do that when a computer can produce it? You don't understand what we're doing. I'm teaching you the vocabulary so that you would hopefully understand complicated sentences. What we are learning now, it's not significant. It's just a word in a very great book that I hope you will try to read. For instance, in terms of philosophy, religion, war, guys, do you know Leibniz, one of the creators of calculus? Do you know that he believed in monads, monadology? Do you know what it is? Has anybody ever been interested in philosophy? That's how I came to mathematics, from philosophy, because I want to grasp concepts. So Leibniz believed that, for example, when you want to clench your fist, right? The fist does not clench because you wanted. It's just that your wishes and the clenching of the fist were synchronized like two clocks. Your soul and your physical body are not connected, they are synchronized. Like this, synchronized. Do you understand why he believed that? I'm not sure if he actually believed in anything. He was a diplomat, a politician, in many things, but why would he postulate such ideas? At his time, religion is very important. You see, not much, not much before that time, people were burned at the stake for heresy, right? During Shakespearean times, if your belief is not exactly right, you will be burned at the stake. Do you understand that? So religion was extremely important to those people, and they believed in the immortality of the soul. But do you know what those little derivatives tell you? If I know the position of all the bodies, all the particles, and their momentum is conserved. That's a consequence of Newton's ideas, of Newton's third law, which is stated in terms of derivatives. You understand? The momentum has mass and velocity. Velocity is the derivative of position. Now, if I know the position of all particles and their velocities, I know your history and I know your future. You understand? Your mechanics tells you that your history is predictable and your future is predictable. If I know at this moment where everything is, I know what would happen in the future and what happened in the past entirely, clearly. Right? And there is no place for the soul there, because if you're built of particles, they're already doing what they are. But the soul is, I mean, you have to have the immortality of the soul. So where do you put it? Leibniz decided, oh, if I have to put it somewhere, then it's synchronized. It cannot have an effect on physics because it's already moving. It's already determined. The particles are there. The soul cannot have an effect. Okay, so truly what it already does, it brings materialism. It brings the doctrine of materialism, strong materialism, into view. It makes it very difficult to believe from the point of view of mechanics that the soul is immortal, that there is even such a thing as the soul. Maybe you're not religious or not philosophers, guys. I'm just showing you the point, the weight of those ideas. Everything that you're using was influenced by such ideas. Physics blossomed. And how did it blossom? Calculus was the engine that powered it. You understand? At least it was the ideas of physics were expressed in calculus. That's why Newton thought about calculus. And if you study physics without it, that I don't believe that you understand physics. And I would like to show you those ideas or teach you to understand it. Right? And those equations, find the derivative short or long way, that's not important. That's not what we're trying to do. We're trying to be interesting and we're trying to be sharp. And if you don't care even about that, guys, you understand that to me, the 500 pages of that book looks like one page. I can summarize calculus in 2 lines and everything else is a quick derivation, at least at the level that we're teaching it. Right? You can have the same perspective of it. It can be condensed and archived like a grain of sand. All right.
Wait, can I say something?
Go ahead.
I know you guys don't know me, but that's okay. Arkady's actually trying to make you guys think of what's actually going on in this like math problem. So like, I know he's like rambling. That's because he's a teacher and nobody's saying anything, right? But he's honestly trying to make you think. You gotta ask yourself like, why am I finding the limit of x going to zero minus or zero plus? There's a certain purpose to that way of thinking. Why am I getting 2 functions x and a, minusing that x minus a over x minus a? It's a process. Once you do that, right, you realize that you're finding something in between a certain equation. Why would I minus and divide an x and an a? Because I'm finding something in between that, or something infinite between those lines. So don't take it for granted, because he knows what he's talking about, and you know, he's honestly trying to make you guys think. So please, you know,
Oh,
try to learn. So
thank you, James. You're gonna make me blush. So I don't know what I'm trying, guys. Do you think I'm rambling? Perhaps I am, right? I hope you can hear at least parts of what I'm saying. And anyhow, guys, so we will call it. I see some people already left. So I will stop the video. And what we do, guys, if you're interested, we can play one what when we're around. There is one easy question I think I have if you want to. And if not, yes, what if you don't, then I will, yeah, then I will just answer your questions. We can practice taking the derivative and everything like that. Okay, guys?